I'd like to talk about sectional curvatures for statistical structures. Sectional curvature is one of fundamental notions in differential geometry, but it's attributed to Riemannian or pseudo-Riemannian structures. For any linear connection, we have its curvature tensor. But to assign a number to a vector plane in a tangent space seems to need a metric. Moreover, the connection and the metric should be related in a good manner. And this happens for statistical structures. I will begin with recalling some definitions and introducing some notation. Okay. So the first definition, which has arisen in statistics, the youngest one, says that you have an open subset of Rn, we have a probability space, and we have a probability distribution, and using the expectation relative to the probability measures, we can define the Fisher information tensor field and a cubic form. So finally, we have a pair consisting of G, a metric tensor field, on M, and a cubic form. This can be immediately extended to manifolds. In differential geometry, statistical structures are also called Curvature structures. So we have a manifold, we have a metric tensor field. I'll assume it's positive definite during my talk. And we have a totally symmetric 1 free tensor field on M. So we have more or less the same as before. Then, using the musical isomorphism, we can replace the cubic form by a 1-2 tensor field, let's say K, which is symmetric itself, and it's symmetric relative to G. And the relation between C and K is as in the last line of the slide. Now, the third definition says that we have a pair, G and nabla, where G is, as before, a metric tensor field. Nabla is a torsion-free connection such that nabla xg of yz is symmetric in x and y. And nabla is called a statistical connection in this case. If we adopt the convention that for any tensor field T of type PQ, nabla T is of type PQ plus 1, where the direction of the covariant derivative nabla xt, x is put in the first place in the sequence of arguments of nabla T, then nabla G is just a zero-free tensor field which is totally symmetric in the case where we have a statistical structure. I'll denote by nabla hat the Levi-Civita connection for G. Then we can take the difference tensor between nabla and nabla hat. I'll denote it by K. And we have the structure as a minute ago. And the relation between the three structures, they are equivalent, is given in the last line of this slide. A statistical structure is trivial, even only if K is equal to 0, or equivalently C is equal to 0, or equivalently nabla and nabla hat coincide. K x of y will stand for K of xy. Okay? Now we can define the mean difference tensor vector field on M, which is the trace of K relative to G. So the structures without mean difference vector field are very important, and we call such a structure a trace-free statistical structure. What is nice in the geometry that a statistical structure G nabla is trace-free if and only if the volume form determined by G is a parallel relative to the statistical connection. Examples. The oldest example, I think, is from the theory of hypersurfaces in Rn plus 1 in the Euclidean space Rn plus 1. So if we have a locally strongly convex hypersurface, or I've forgotten, a locally strongly convex hypersurface in Rn plus 1, Then we have the second fundamental form, which in this case is, let's say, a positive definite, and it satisfies the Curvature equation, where nabla is the induced connection. That means the Levi-Civita connection for the first fundamental form. The pair H nabla is a statistical structure. Similarly, one gets statistical structures on hypersurfaces in space forms. The second example is also quite old, at least more than 100 years old. So the equi-affine geometry of hypersurfaces in the standard affine space Rn+1. Again, we have a locally strongly convex hypersurface in Rn+1. We have a transversal vector field, not necessarily metric normal or relative to any metric. We have the standard flat connection on Rn+1, and for any vector fields xy on M, and with a fixed transversal vector field, we can split the dxy into the tangential and transversal part. This tangential part, which is denoted by nabla xy, defines a torsion-free connection nabla, which is the so-called induced connection. H is the second fundamental form, which in this case, again, is a metric tensor field. And then we can differentiate psi relative to x. Again, we split it into the tangential and transversal part. And if the transversal part vanishes, then a transversal vector field is called an equi-affine transversal vector field. In this case, we have the Curvature equation, again, as in the Euclidean or metric case. So again, we have a statistical structure. So here a small, just few pictures. So we have a tangent space, we have a transversal vector, we have a field of transversal vectors. Now I'd like to mention two examples when the transversal vector field is equi-affine. This is the case where the lines determined by a transversal vector field are parallel. The induced structure on this hypersurface, on the surface, is Curvature, statistical. Okay. The next picture is when the lines determined by a transversal vector field meet at one point. Such a hypersurface is called centro-affine, or a proper equi-affine sphere, or if the induced structure is trace-free, it's an affine sphere, a proper affine sphere. In the last case, with the case with the parallel lines, we say about improper affine spheres. So I would like to emphasize here that the class of affine spheres is huge and still very mysterious. So there is a lot of examples and almost no chance to characterize all of them. So here, the last source I'd like to mention, the source of statistical structures, is the theory of Lagrangian submanifolds in Keller manifolds. So we have a Keller manifold of real dimension to M with a complex structure J. We have a Lagrangian submanifold of M. That means it's a real n-dimensional submanifold such that J of Tm is orthogonal to Tm. So it's the normal bundle. J of Tm is the normal bundle for M. If D is the Keller connection on N, then again we can decompose dxy, where xy are vector fields on M, into the tangential and transversal part. The transversal part can be written as J composed with kxy, where k is a 1-to tensor field on M. And again, we get a statistical structure on such a submanifold. And this structure is trace-free if and only if the submanifold is minimal in N. Most of statistical structures outside the three classes of examples. For instance, in order that a statistical structure is locally realizable on an equi-affine hypersurface, it is necessary that the dual connection is projectively flat, which is a strong assumption, and now I'll recall the definition of the dual connection. It has been used today, but I will use my notation here. So if we have a metric tensor field on a manifold M, then for any linear connection, we can define its dual connection by the formula number 2. So it's clear from this that the Levi-Civita connection is just self-dual. If we have a statistical structure G nabla, then the dual structure G nabla bar is also statistical. Denoted by R, X, Y, Z, the one free curvature tensor for nabla, and by R bar, X, Y, Z, the curvature tensor for nabla bar. The two curvature tensors are related by the formula 3. So we see that, in particular, they simultaneously vanish or not. Now, I'll denote, okay, so we have the Levi-Civita connection. We have the difference tensor for nabla, which is K, and we have the difference tensor for nabla bar, which is minus K. Using this, we can find relations between curvatures, curvature tensor for nabla, nabla hat, and nabla bar. Look at the formula 4, and on the right-hand side, we have the curvature tensor for nabla hat. We have the part with this portion in the middle, which is the skew symmetrization of nabla hat K, and we have the bracket on the right hand, on the very right side. And so we have the bracket is just the commutator of Kx and Ky. The same formula can be written down for nabla bar. We just replace K by minus K, and we have the formula and the last but one line of the slide. When we add these two formulas, we get the formula number 6, which says that R bar plus R is equal to twice R hat plus the commutator of K's. Now, let's say the curvature tensor R does not have to be skew symmetric relative to G. That means, in general, we have this inequality written here. But the case where we have the equality is also very important. It corresponds to the case of affine spheres. I have the lemma star, which is important for my talk, but very easy to prove. The following conditions are equivalent. The curvature tensor for nabla is skew symmetric relative to G. R is equal to R bar, and nabla hat K is symmetric. So let's consider the curvature being the average of R and R bar. I denoted it by script R. And the second tensor of type 1,3, that means the bracket KK, which is defined as the commutator of KX, KY acting on Z. Both these tensors are Riemann curvature-like tensors. That means they are skew symmetric in X and Y, satisfy the first Bianchi identity, and they are skew symmetric relative to G. So having this, we can just copy the procedure from Riemannian geometry, and we can produce sectional curvatures. The first sectional curvature I mentioned here is just the ordinary sectional curvature. We have a plane in a vector plane in TXM in the tangent space. We have an orthonormal basis of it, and we have the sectional curvature. The second curvature, the sectional K curvature, is for the tensor field K. So we have this curvature defined by the commutator, by this bracket. And the sectional nabla curvature connected with the connection nabla, and this is for the curvature tensor script R. What is nice, maybe, non-trivial, that in general, Schur's lemma doesn't hold for K nabla and K for these two curvatures. However, we have some situations when it holds. For instance, assume that M is connected of dimension greater than 2, and the sectional nabla curvature or the sectional K curvature is pointwise constant. If one of the equivalent conditions in lemma star holds, then the sectional nabla curvature or the sectional K curvature is constant on M. Now I'd like to concentrate on the sectional K curvature. The easy situation which should be taken into account is when the sectional K curvature is constant for all vector planes in a tangent space. In this respect, we have this theorem. So if the sectional curvature is pointwise constant, so is constant and equal to some A for all vector planes in TXM, then there is an orthonormal basis, E1, En of TXM, and the numbers lambda 1, lambda n, mu1, mu n minus 1, such that the matrix representation of K is as here. Okay? So we have the first matrix is diagonal, and the others are produced in such a way that, let's say, you see here, we have lambda I, mu I, mu I, mu I, and the rest is 0, and in the ith row and ith column, we have mu1, mu I minus 1 because of the symmetries of K. What is important here that the representation is not unique. So in some sense, in the procedure of getting it, we choose lambdas. But the numbers are related with each other. And the important fact is that if the statistical structure is trace-free, then they are unique. The representation is unique, and the lambdas and mu's depend only on the sectional curvature and the dimension of M. Now, it was made pointwisely. So I can do this at each point, but it's not true that it's possible to do it around each point. The difficult points are, if they are, let's say, isolated, are points where the representation is like here. So we have only one parameter, lambda, and in the first matrix we have lambda, lambda half, and then all zeros except for the places where we have to have lambda half because of the symmetries. So if lambda is not 0, if the structure is not trivial, then the sectional K curvature is constant and positive. Another example, of course, we should consider the case when this K sectional vanish. In this case, there is a normal basis such that the representation is like here. So we have n parameters, lambda 1, lambda n. They are in suitable places. They can be 0, not 0, everything. Then I like to present some theorems on the sectional K curvature. For instance, we have a trace-free statistical structure on M with symmetric nabla hat K. If the sectional K curvature is constant, then either K is equal to 0, that means the structure is trivial, or the underlying Riemann structure is flat. Another theorem says that if nabla hat K is 0, then each of the following conditions implies that the underlying structure is flat. That means the sectional K-curvature is negative. It doesn't have to be constant in this case. And the second condition is that the K-sectional curvature vanishes and K is non-degenerate. That means A to Kx, the mapping is a monomorphism. Another theorem says that if K is as in example 1, that means this example with lambda, lambda half, and so on, at each point of M, and if nabla hat K is symmetric and the divergence of the mean difference vector field is constant on M, then the sectional curvature for G by any plane containing E is non-positive. If, moreover, M is connected, then it's constant. If this vector field E is parallel, then the sectional curvature by any plane containing E vanishes. Another theorem says that if we have a statistical structure for which the sectional K-curvature is non-positive on M, and the bracket Kk acting on K as a differentiation gives 0, then the sectional K-curvature vanishes on M. Here is a corollary, but let's skip it. If the sectional K-curvature is negative on M and R hat acting on, as a differentiation on K gives 0, then the underlying structure, metric structure, must be flat. Let's skip this and let's go to this. So we have another type of sectional curvature. Here I'd like to present two theorems very shortly. So we have a lot of examples where the nabla sectional curvature is constant. Namely, we have all affine spheres. But I'd like to say a few words about the curvature operator. If we have a Riemann curvature like tensor, then it defines the curvature operator. That means it's a linear operator acting on the second exterior power of the tangent bundle into itself. So if, for instance, we will take this curvature tensor script R, we can produce what I denoted here by the fracture R, we can produce the curvature operator. The assumption that the curvature operator is positive definite is stronger than the assumption that the sectional nabla curvature is positive. So here I like to mention two theorems. Assume we have a connected compact oriented manifold and we have a trace-free statistical structure on M. If R is equal to R bar and the curvature operator determined by the curvature tensor R hat is positive definite on M, then the sectional nabla curvature is constant. And another theorem, let M be a connected compact oriented manifold and we have a trace-free statistical structure on M. If the curvature operator for script R is positive on M, that means positive definite on M, then all Betty numbers except for the first and the last one are 0. So here are the references. No. Oh, yeah, I have only one remark. So it's nice that the ordinary sectional curvature also influences the geometry of statistical structure, okay? So for instance, we have such a theorem. Let M be a compact manifold equipped with a trace-free statistical structure such that R is equal to R bar. If the sectional curvature K hat for G is positive on M, then the structure must be trivial. In the two-dimensional case, we have better results. For instance, let M be a compact surface equipped with a trace-free statistical structure. If the genus of M is 0 and R is equal to R bar, then the structure must be trivial. And so these are examples of theorems. Here are references for my talk. Thank you very much.